Getting the expected output using artificial intelligence is challenging, and doing it in optimized way is even more challenging. Optimization is a crucial topic in artificial intelligence. I'm Nuruzzaman. I teach artificial intelligence in electrical engineering and computer engineering departments. And in this lesson, I'm going to cover hill climbing algorithm, one of the optimization algorithms we use in AI. The first part of this lesson covers the theoretical concept. And in the second part, we're going to implement the theoretical concept using Python programming language. It is a very interesting lesson. As a matter of fact, any engineering topic is interesting. If you don't feel the same, if you think that engineering is boring math, then you are at the wrong university. Switch immediately. Alright, let's get started. A problem can be solved in different ways. However, we do not want all of the solutions. We want the optimized solution. For example, an AI agent wants to go from here to here. There are multiple paths to do it. Any of this path will lead to the desired destination. Suppose the AI agent chose this route. Without any doubt, this is a solution to this problem. However, it is not an optimized solution. We understand simply by looking at these options that this is the best way to reach the destination. And choosing the best option from a set of possible options is called the optimization. If we appoint an AI to optimize something, it will search for the best solution. That means optimization is a search problem. The search algorithm we use for optimization is called local search algorithm. Local search is a search algorithm that maintains a single node and searches by moving to neighboring nodes. This type of search algorithm is different from regular search algorithms such as depth first search, breadth first search, A-star search, etc. These algorithms try to find out the quickest way to the goal. On the other hand, local search is interested in finding the best solution to the problem. It may not always be possible to find out the best solution. However, local search algorithm will bring at least good enough solution. We can see a configuration of houses and hospitals here. And these are the distance from the houses to the hospital. Observe here, this house is close to the hospital. However, this one is far away. Here, both of the houses are far away from the hospital. The question is how to place the hospital in such a way that ensure minimum distance between the hospital and the house. So we're trying to figure out the best location of the hospital to minimize the distance. So without any doubt, this is an optimization problem. That means we have to use local search algorithm to solve this problem. We're trying to minimize the distance. So let's calculate the distance first. We will use Manhattan distance here. I believe you remember that the Manhattan distance between 2 points measured along axis at right angles. That means this is the distance from this house to the hospital, and the distance is 3 units. The distance of the hospital from this house is 6 units. Here the distance is 4 units, and here it is 4 units as well. to gather 17 units distance. The optimization goal here is to minimize this distance. It is easier to visualize problems in images. However, to apply optimization algorithms, we have to be a bit mathematical. We can represent this house and hospital configuration using a state space landscape. It is actually a bar graph. Each of the bar represents a specific state, and the height of the bar represents the distance unit. For example, this state is represented by this bar, and the height represents the distance unit. Let's change the configuration a little. This time the total distance is 11 units. For this state, the total distance is 13 units. This is how we generate a state space landscape from different configuration of a problem. Now we can design an optimization algorithm using the state space landscape. Suppose this is the state space landscape of all possible configurations. We can see that this configuration minimizes the distance, and this configuration maximizes the distance. Suppose this is our current state, and we want to minimize the distance. Then we have to travel in this direction. The immediate left and right states are called neighbor states. Here we are to move to this neighboring state. After that, here. So we are at the optimized state. Now getting the minimized value is not always the case. In many situations, we want to get the maximum value. For example, selling a house. If you are the seller, your goal is to sell the house at maximum price. So in this case, optimization goal is to find the state that maximizes the price. The function that looks for the minimum value is called the cost function, and the function looks for the maximum value is called the objective function. In our example, we are trying to minimize the value. That means we will use the cost function. Now we know a lot about this state space landscape, and we are ready to develop an algorithm to optimize distance among houses and hospitals. So our goal is to minimize the distance. That means we are going to use the cost function. This is our problem space. So this is the input to the algorithm. The algorithm reads the initial state as the current state, then it explores the neighbors. If the neighbor is the best valued neighbor, if the neighbor state is lower than the current state, then the neighbor will be the current state. If not, the current state will remain as it is. That means we will return the current state, and we will keep repeating it till we get the minimum value. So this is our optimization algorithm, and this algorithm is called hill climbing algorithm. The hill climbing algorithm is one type of local search algorithm because the neighbor states are compared to the current state, and if any of them is better, it changes the current node from the current state to that neighbor state. Now the question is how to define the better state. What qualifies as better is defined by whether we use an objective function or a cost function. We have already learned that objective function prefers a higher value and the cost function picks a lower value. If we want to minimize something, then we will use cost function. That means the better state will be the state which is lower than our current state. On the other hand, if we want to maximize something, then we will use objective function, and in this case, the better state is the state which is higher than the current state.
It is time to implement the concept. We're going to use Python programming language to do it, and definitely we're taking an object-oriented approach. First of all, we will define a class named space. Then we will construct the addHouse method to add house on the problem space. After that, we will create an available space method to find the available location to place the houses and the hospitals. Then we will construct the getCost method to calculate the distance as cost. After that, we will develop the getNeighbor method to find out the valid neighbors. Then we will create the outputImage method. This method is not the part of the optimization. I want to show you the output graphically. That is why we will use this method, and I'll be real quick in this section. I'm just going to show you the code with quick explanation. After that, we will construct the hillClimb method to optimize solutions. I will explain everything in details in this section. Finally, we will create an object of the space class and generate some optimized solution. You can download the code using the link given to the description of this video, but I recommend you to type with me if you really want to learn.
First of all, launch the PyCharm. It is loading. PyCharm will take some time in the beginning to initialize. Let's wait till it gets ready. The PyCharm is ready. Now click on this File. Then choose this New Project. The New Project window will open. We're going to choose the working directory from here. For that, click on this Browse button. The directory selection window opens. The directory you will see here will be different from my directories. I'm going to save the project under Lesson 4 Optimization folder. Click on this New Folder icon to create a new folder. Give it any name you want. I'm naming it The Code. Now select this folder and click OK. We can see the location of the project in our selected folder. Now click on this Create button. We're going to open the project in this window. Again, PyCharm will take some time to create the virtual environment. Now it is ready. Right-click on the name of the project directory. From here, choose New and then click on Python File. Now we need to name this file. Let's call it Hill Climbing. Then hit Enter from the keyboard. You can see the Python file is ready. We can start coding here. However, before that, we need to prepare some images and fonts. Don't worry about it because I've already prepared those for you. You can download them from the link given in the description of this video. Now right-click on the project directory and go to Open In. Then click on Explorer from here. This is our project directory. get inside of this folder. Here I'm pasting a folder named assets. Again, don't worry about this file. You can download it from the description of this video. This folder contains two more folders. One is for images. Here you can see the images of the house and hospital, which we will use in this project. And here is the font we are going to use. Now we can close this folder. In this project, we will implement a hill climbing algorithm to optimize the distance between the houses and the hospitals. And we want to show it graphically. That means we need to generate the images. To work with the images, we need to use the Python Pillow library. It is a popular library for the image. To install it, go to the terminal window and type in pip install pillow. Then hit enter. The installation process will start, and we can see it has been successfully completed. All set. Now we are ready to start coding. Minimize the terminal window and collapse the project panel to have a little larger space to code. In the beginning, import the random module. We need to randomize a lot of things in our project. That is why we need this random module. Then define a class and name it a space. You can choose any other name. However, there is a reason behind choosing this name. This is our problem space, and we're trying to optimize the distance on this space. So this name reflects the situation. That is why I'm choosing this name. Again, you are free to choose the name you want. However, maintain the naming convention. Capitalize the first letter of a class. This space is defined by height and width. There are a number of hospitals too. That is why in the constructor we're specifying the height, width, and number of hospital parameters. Then under the constructor we're initializing them. We need the houses and hospitals too. And they have been declared as sets. So the class constructor is ready. We can see a warning here. There is nothing wrong with our code. PyCharm wants us to use 2 line breaks here to enhance the readability of the code. Let's make PyCharm happy by adding another line break here. Now the warning is gone. On the problem space, we need the capability to add houses. For that, we are defining a method named add_house. And the parameters are row and col, which is the short form of column. The location, or we can say the coordinate on this space, is specified by row and column. That is why the parameters are row and column. It will simply use the add method and will add the row and column pair in the houses set. That's it. With this method, we have gained the capability to add houses to the space. However, if a house or hospital is already there, we cannot add anything to that location. So we need another method to find out the available spaces. Let's call this method available_space. These coordinates, or we can say the blocks, are the candidates. So declare a set named candidates. It contains the row and column pair. We have already learned that this row-column pair is the coordinate. That means they represent these blocks. Run a for loop along the height of the space to get the rows, and another for loop along the width to get the columns. Now all rows and columns are here. We don't want all of them. We only want the available space. That means if there is any house or hospital on the block, we need to remove that block from this candidate set. Use another for loop to iterate through the houses, then remove the coordinate of the house from the candidate. Do the same thing for the hospitals. Finally, return the candidates. Now this candidate set contains the location of the available space. Now we need a method to calculate the cost. By cost, I mean the distance between the house and the hospital. Let's define a method named get_cost, and the parameter is the hospitals. Initialize the cost variable to 0. Now in a for loop, type in cost variable, then use augmented assignment operator to keep adding the costs. To get the cost, we'll iterate through the houses and calculate the distance of house from the hospital. So take the x-axis difference between the house and the hospital. Here 0 means the x-axis. That means the row value. Sometimes this difference can be negative. Use the absolute function to always get the positive value. Do the same for y-axis. Here this 1 means y-axis or column value. We need the minimum cost, so use the min function here. This method receives the hospitals, which is a set. To calculate the distance, we need individual hospital, not entire set. So use a for loop here, iterate through the hospital set, and access one hospital at a time. Finally, return the cost. From the theoretical explanation, we have learned that local search explores neighbors. That means we need to get the neighbors. So define a method named get_neighbors, and the parameters are row and column. In our problem space, the locations are specified using rows and columns. That is why these are the parameters of this method. Now define a list named candidates. In this list, we will include the neighbors. Now think about a location. From here, the neighbors are up, down, left, and right. To go up, we have to subtract 1 from the current row, and the column remained untouched, because the column is not changing. To go down, we have to add 1 with the row, and again the column remains as it is. However, if we want to move left, we need to subtract 1 from the column, and the row remains as it is. To move to the right, we need to add 1 with the column, and again row remains untouched. Now declare another list named neighbors. Not all candidates are neighbors. For example, from this location, there is a house here. That means this space has been occupied and it cannot be a neighbor. Again, think from this point. There is no neighbor outside of this problem space. So we have to make sure that these locations are not picked up as neighbors. To do that, we have to iterate through row and column using for loop. Then if RC in the houses or in the hospitals, in other words, if the row and column belong to the house or hospital, then we will continue. Nothing will happen. On the other hand, if R is greater than equal to 0 or less than the height, and C is greater than equal to 0 and less than the width, then append RC to the neighbors list. And finally, return the neighbor. Now it is time to define a method to generate output image. Let's name it output underscore image and the parameter is file name. To work with images from PIL, we need to import image, image raw, and image font module. I'm not going to explain everything in details here because this method is not related to optimization. We are using it to graphically visualize the output. This is the image we're going to create. Let's declare cell size 100 pixel, cell border 2, cost size 40, and padding 10. Now use the new method of image module to create an RGBA image. This is the size of the image and color is white. There are houses and hospitals on the image. There are some text here as well. So we need to load the images and paste them here. Let's load the image of the house. It is inside of the image folder, which is inside of the assets folder. Resize the image according to the cell size. Do the same thing for the image of the hospital. Load the fonts too. Then use the draw method of image draw module to draw the image. Now use a nested for loop to iterate through this 2D space and place these rectangles on it. Here, this rect is a list. The size of the rectangles is defined here. Use rectangle method of draw module to draw the rectangle and fill it with black color. If the IJ, that means the coordinate, belongs to the house, then copy the house, target the rectangle and paste it there. Do the same for the hospital. If the coordinate belongs to a hospital, then copy the hospital, target the rectangle and paste it there. Then draw the rectangle with this shape. After that, draw the text which will print the cost in white font. And finally, save the file. Now it is time to develop the hill climb method. The hill climbing algorithm compared the value of the current state with neighboring state iteratively. To control the maximum number of iteration, we are taking a parameter named maximum here. Initially set it to none. We want to generate graphical outputs. There will be multiple images. To track them, we will use same image prefix and initially set it to none. We also want to track the log. Here log refers to the optimization progress. Initially set it to false. We will change the value later on when we will have called this method. So, the hill climb method definition is completed. Initialize a variable named count to 0. Then use the hospital set that we declared in the constructor of our space class. Now we are going to add the hospitals randomly on the available space. Start with the for loop to iterate for the number of hospitals. Inside of this for loop, type in self.hospitals. Then use the add method. We want to insert the hospitals randomly. So, use the choice method defined in random module. We need the hospital's information as a list. That is why use the list function here. Then use the available space method. We developed this method earlier. Remember? If the log is true, then we want to print initial state :cost. To get the cost, use the get_cost method. This is also our self-defined method, and it takes the hospitals as the input argument. So this line will print the initial cost. If the image prefix parameter is true, we will use output_image method. We have seen that this method requires the file name. There will be multiple images, so we need to name them dynamically. If we keep the same name, then new image will replace the old image, and at the end of the day, we will get only one image remaining. To dynamically generate the image name, we are using f-string format here. The first part is the image prefix, and it does not change. The count part will change. We can see that this count is a number, but we need a string for the file name. That is why we used this string function here to convert the number into string. And this z field with argument 3 is filling the file name with 3 zeros. That means we can generate 1000 image names starting from 000. Finally, write the image extension. You can use any extension. However, I prefer using PNG. Initiate a while loop. The loop will run as long as maximum is none or count is less than maximum. That means if we pass the maximum value, then it will keep looping till the count is less than maximum. If maximum is none, that means nothing is passed to parameter, yet this loop will run. In every iteration, increase the count by 1 using augmented assignment operator. Then declare an empty list named best_neighbors and use a variable named best_neighbor_cost, and the value is none. Now we need to iterate through the hospitals using a for loop. Inside of this block, we need another for loop to find out the neighbors of the hospital. Now declare a variable named neighbor and copy everything from the hospitals. Then remove the hospitals we have iterated and add the replacement to the neighbor. After this, we need to calculate the cost using the get_cost method, and the argument is the neighbor. I understand this section is a little confusing. You are thinking that why we are removing the hospital and then again adding the replacement. Let's try to understand it from here. We are iterating through the hospitals. That means we will get the location of the hospital. Then we are looking for possible replacement in this for loop. Possible replacement means the neighbors which we are getting through this getNeighbor method. We can see these are the neighbors. Now we are copying everything we have in the hospitals in the neighbor. After this line, we won't touch the hospitals. We will work on neighbor. Once we have the information about the neighbors, we remove the hospitals from the current location and add the replacement to new location. Finally, we calculate the cost. Now is it clear? If not, you can ask a question in the comment. And the door of my classroom is always open for everyone. Just get in, follow the lectures, and ask question if you're confused. Now, if best neighbor cost is none or cost is less than best neighbor cost, then best neighbor cost is the cost and best neighbor is the neighbor. Here we're using third bracket because we want to store it as a list. Else, if the best neighbor cost is equal to the cost, then append neighbor to the best neighbors. Our work inside of the nested for loop is completed. Now get out of the nested for loop. If best neighbor cost is greater or equal to the cost of the hospital, we are using get_cost method here to calculate the cost, then return hospitals. That means nothing will happen. On the other hand, that means if the best neighbor cost is less than the cost, then this else block will be activated. And in this block, if the log is true, using f-string formatting, print found better neighbor cost. Then in the placeholder, put the best neighbor cost. Outside of this block, randomly choose the location of the hospitals from the best neighbors. If the image_prefix is true, use the output_image method like we did before. It will generate PNG image with the prefix and with 3 digits. Alright, our space class is ready. Let's create an object of the space called S. The height is 6, the width is 12, and number of hospitals are 2. Now use a for loop with range 5. That means this for loop will iterate for 5 times. Now use the add_house method of the S object. The house will be placed randomly. We are using the randRange method of the random module. The input argument to this method is the height of the problem space. Do the same thing here. These two arguments together represent the random coordinates of the problem space. As this loop will run for 5 times, 5 houses will be added on the problem space. After that, use a variable named hospitals. Then access the hill_climb method. The image prefix is hospital and log is true. We're not specifying any maximum iteration here. Now this method will return the optimized hospital location. Expand the terminal window, then run the program. We can see initial cost is 28 and the optimized cost is 9. Expand the project panel. We can see the images have been generated here. Right-click on any of these images, go to Open In, then click on Explorer. We can see the generated images. Let's open the first one. You can see the name of the image is hospitals000.png. This is exactly how we coded the name of the images. Now use the left arrow to load the next image. We can see the location of the hospital changes and the cost keep getting minimized. According to the algorithm, this is the optimized orientation of the hospitals. that minimizes the distance between house and hospital from any house. Rerun the program. This time the initial cost is 17 and the optimized cost is 9 again. Let's open the image directory again and load an image. This is the initial state and this is the optimized state. Let's run the program once again. The initial cost is 26 this time. Last time the optimized cost was 9 and this time it is 15. That means the last configuration was better than this one. So without any doubt, the hill climbing algorithm will not give us the best result every time. However, it tries to generate a good enough result, but it is not guaranteed because there are some limitations of this algorithm, and that's what we're going to cover in the next lesson.
Did you enjoy the lesson? Could you learn properly? Please give me your feedback. Based on your feedback, I will further develop my teaching method. And if you are having poor learning experience in your university, leave me an email with the topic you are struggling with. Whether the topic is related to computer science and engineering, electrical engineering, software engineering, information technology, or telecommunication engineering, I can help you. I'm an electrical engineer, major in telecommunication with a master's degree in information technology with 4 out of 4 CGPA. If you need my help, email me. If you like to read from book and learn from books, you can read my book. I've written one book on image processing and there is another one on cloud computing. And if you want to attend the class physically, my classroom is always open for you.